As I was saying, we're going to talk today about 3D printing of silicon carbide with our Zetamix technology. So this is the latest material we've just launched. Of course, I'm sure most of you are familiar with both the company and the technology, so I'm very sorry for those who already know. I'm just going to do a few reminders for our newcomers about who we are and what we do in additive, and then we'll dive in precisely silicon carbide material. So the first thing is a few very quick words about Nanoe. Just to say that Nanoe is a material company. Our job is to provide high performance ceramic raw materials to technical ceramic manufacturers, both for traditional process like injection molding or pressing, and also materials for 3D printing. So we are a relatively small company. We're really focused on high performance material with, let's say, a small scale. What we call small scale is 100 kilo to 1 ton of material per batch, and a typical production of a few tens of tons per year. That's it for the company. I just want to focus on one thing, which is really we are a material company. We're not a printer manufacturer, we're a material company, and that's where we come from when we develop materials for 3D printing. So the company has been active for almost 15 years, and more recently in 2018 we started the line of ceramic filament with the objective to really make ceramic and metal printing affordable and easy to use, so that we could democratize access to these materials. So that's why we decided to go for what we call FDM or FFF printing, because it allows for a low cost, easy to use technology, and we can still manage to have high performance material with this technology. So we are a material company again. So what we offer is mainly materials. We offer them in the form of spools or filaments, ceramic filaments first, so alumina and zirconia black and white. The new one is silicon carbide, of course. And then we also have some steel filament with a stainless and a tool steel filament. We also, through some partnerships with manufacturers of equipment, we also offer compatible equipments that allows to print these materials, mainly a printer and a sintering furnace, which are the two main steps. There's also a small debinding kit, because in some case we need chemical debinding. But again, we do offer these equipments because we know that some customers want the full solution. But again, we are a material company, so the focus on our side is on developing new materials and improving the materials, and not necessarily the printers. So how does that work? Well, basically, if all of our filaments, they are actually composites. That means you have a powder, which is the materials we want to print. But in order to be able to print it, we need binders, and that's what allows us to make the filament and then to print it on any FFF FDM printer. So the binder is actually a set of several binders, some of them being here really as a backbone to hold the powder together, and some others being there for other functions. Usually one of them can be soluble in a solvent and the other one not. And the fact of having several binders will allow us to have all the necessary properties of the filament. And then the process is quite simple. For ceramics, we will go through a 3-step process, which is very well known for ceramic manufacturers, and who's also starting to be well known in 3D printing. So we print by using any FDM printer on the market, and then we debind chemically. So we dip the part in acetone in this case, and then we will sinter the part under air. And when I say sinter, it's actually thermal debinding, because there's still a bit of binder in the material, and sintering in a furnace. If we talk about metal, it's slightly different. We don't have any chemical debinding. All the debinding is done in the furnace, which makes the process a bit more simple. Clearly, you actually have 2 steps. You print and then you put in the furnace. and in the furnace you'll have deep binding and sintering. However, the sintering needs to be done under protective atmosphere because, of course, if you don't do that, the metal will oxidize and you won't get a good material afterwards. So for H13, it's done under argon. We also have a stainless steel which needs hydrogen, but it's a bit more complex. So now a few words about silicon carbide and what is that material, what are the properties, and why do we want to print it? And then we'll dive into the technology. So silicon carbide is really a high performance material. It's a material that you see in advanced applications a bit everywhere. You'll see it in aerospace, you'll see it in semiconductor, you'll see it in a lot of high performance applications because of these properties they have. It's a very light material with a low density, very hard, one of the hardest material available on Earth. It's high temperature resistant, so the range of temperature is quite wide because it depends on the atmosphere, but it's high temperature resistance. It does have some semiconductor properties. So in our case, clearly, it's not the kind of silicon carbide used for semiconductor, but however, it does mean that the material can conduct electricity. It can be used as a heating element, for instance. It's very corrosion resistant. It's wear resistant. It has a very high thermal conductivity. You see that there's a lot of attractive properties here, which makes it a material that you could think should be everywhere. The reason why it's not everywhere is that it's an expensive material. It's expensive because the raw materials themselves are relatively expensive. They cost a lot of energy to produce. And then the sintering cycles are also extremely expensive because you need very high temperature and vacuum sintering. So the whole process line to make the material and to sinter the material are very energy intensive, and so they cost a lot. And at the moment, they particularly cost a lot because energy prices are soaring. So it is the reason why silicon carbide is actually more like a last resort material. We print in silicon carbide when other materials won't be good enough. And typically, for us, the low-cost version of silicon carbide would be aluminum oxide. It's a bit similar in properties. It's lightweight. It's very hard. It's relatively chemical resistant. But in some cases, alumina won't be strong enough, won't be light enough, won't be corrosion resistant enough, and that's where we will go for silicon carbide. A few words about silicon carbide and the different specificities, the different qualities of silicon carbide available, because that's something of importance in that case. Because of this very high temperature sintering, there's been a lot of work done into developing nuances of silicon carbide that can be sintered at lower temperature, and that means when we say silicon carbide, a lot of people may have a different definition of what is a silicon carbide. So you have everything from some porous material that are just sintered at low temperatures and will be used for catalysis or for filtration and doesn't actually need to be dense. And up to the fully dense sintered silicon carbide, which is really a pure dense silicon carbide, which is usually sintered around 2,200 degrees Celsius. And in between, there have been a few alternatives that has been developed. One of them is silicon infiltrated silicon carbide, which is also called a reaction bonded silicon carbide. Well, basically, it's a porous SiC in which we will infiltrate some silicon metal to fill the gaps. It does make a very interesting material, but clearly it has a lowest level of performance than a pure dense silicon carbide. And you also have a third quality, which is liquid phased sintered silicon carbide. Basically, it's a silicon carbide with some dopants, which are usually oxides in the range of 10-15%. And these dopants during the sintering, they're gonna end up being liquid, and they're gonna help with densification, which allows to densify at slightly lower temperature again. And the final one is the sintered silicon carbide. So that's the one we're printing in our case. It's really the purest material, even though there are a few dopants in it. There is usually, and in our case at least, there is a bit of carbon and a bit of boron carbide, and that's the only dopants you have in this material. And they are here in very, very low amounts. So why do we want to print silicon carbide? There's a few obvious reasons here. The first one is it's a material that's very difficult to handle. Shaping the material is quite complex, and clearly if you want complex shapes, you really need to do them before sintering, because machining the material after sintering is literally horrible because it's so hard. So it's very, very hard to machine after sintering, so you need to do everything before. And that means if you want to have complex parts, very complex parts, it may be difficult with silicon carbide to obtain these. You will usually do silicon carbide by pressing and green machining, and that will limit a bit the kind of geometries you can do with silicon carbide. So that's why we want to print it. We want to be able to optimize structures, to reduce weight. We want to be able to use the advantage of additive flexibility of the technology, the ability to print one-off parts or a few parts at a time. All of this is very attractive, and it's not really available for the moment in silicon carbide. And one of the reasons why it's not available is that printing a dense silicon carbide, again, that's why I precise dense and not a silicon infiltrated version, for instance. But printing a dense, pure silicon carbide is at the moment not possible with any other technology. That's one of the reasons why we developed those filaments, because it really unlocks some applications where our customers just don't have any technical solution at the moment. So how does it work? Well, it's really very similar to what we do usually. You have file preparation, printing, which is done again with any FDM printer, debinding, which is done in acetone. The one big difference is sintering, and that's the one limit of this material again, is you need to sinter the material at 2200 degrees Celsius under vacuum or argon, and that is clearly one of the drawbacks of the material. So it's a limit, of course, because we don't offer a compatible furnace for this, which means that you either have a furnace yourself, but in that case, you're part of the happy fuse, or you need access to a furnace. So we are considering at Nanoe launching a service so that you can sinter those parts with some of our partners. Depending on how the demand is on that part. But that clearly is going to be the limit. If you are interested in silicon carbide, the first question you should ask is, how am I going to sinter it? Very easy to print, very easy to debind. That's not the problem. The question is, how am I going to sinter the material afterwards? So a few step-by-step explanation here. So the file preparation is again very similar to what we have with any FDM printing. The only difference is we're going to use that step to also compensate for the shrinkage of the part. So typically we have a shrinkage around 20%. I can't remember exactly how much for silicon carbide. It's in the data sheet. And so we will oversize the part before printing. The printing temperature in that case is relatively low. It's around 120 degrees Celsius. Because again, our binders, they're just temporary binders. They don't need any thermomechanical properties. They're just here to shape the part. And in that case, it's a quite low temperature printing. So once we have done the file preparation, we have generated what we call J-code, which is lines of instruction for the printer. We will just print on any FFF printer, and then you debind. In that case, it's a two-step debinding process. The first step is to dip the part in acetone, which will remove approximately half of the binder. And then you will have a thermal debinding, which occurs in the furnace, and then sintering. Usually, the kind of sintering equipment you need for silicon carbide are high temperature vacuum furnaces, and you usually don't want to do the debinding in that furnace. So we actually generally use two different furnaces. We use one for debinding under argon, but typically we could use one of our tubular furnace for that. And then we will use the high temperature vacuum furnace only for sintering. And here on these small examples here of the part at the different process steps, you can understand why the shrinkage is occurring. Basically, if you want to densify the material, the grains have to coalesce together. The powder has to bridge the gap and to fill the porosity, and that's why you are going to have that shrinkage of approximately 20%. So that's the sintering condition, and here you have the shrinkage. So I knew it was here somewhere. You can see there's quite a difference between X, Y, and Z, which happens with some other filaments. It really depends on materials. Here the difference is quite significant. And we reach densities up to more 98%. 99 would be really high for silicon carbide, but 98% is what we can achieve with this material. So that's just a small illustration again of what happens during sintering. We try to insist on this because we know that for some people, sintering is not something you come across very regularly, and that idea of densifying a material without melting can be a bit troubling at first. Well, this is really how you make any ceramic in the world anyway, so that's not new to ceramic manufacturers, but may be a bit newer if you come from a different background. So I know that we've covered a bit how we can print and sinter this material. What kind of application do we have in mind? Why did we develop that material? So, well, we developed it because we had a few OEMs who were really asking for this, and these OEMs are in a few fields that I'm going to talk briefly about. Of course, we're also looking for new application. We're also looking to see what could be other opportunities with this material. So this is not an exhaustive list, it's just what we have identified so far. So the first one is aerospace and optical components. This is really a fact that is really not very well known, but most observation mirrors that are sent into space, typically the James Webb mirrors and also mirrors on smaller observation satellites. Most of these are made in silicon carbide, or a strong half is made in silicon carbide. Why is that? It's because we need a material that is, of course, extremely strong to withstand especially the launching phase. That's where it needs to be the strongest. It needs to be stiff so that it won't deform. You want a light material, of course, because sending weight in space is expensive. You also need a material that will not deform because of temperature differences. In space, of course, you have huge temperature differences between the different zones, and so you need a material that won't deform whether it's hot or cold. And for that, you need a low CTE, and you need material that's heat conductive, so that the temperature will be homogeneous on the whole material. Of course, if it's a mirror, you need to be able to make a mirror out of it, so you need to be able to polish it to a very low surface roughness. After that, you will have some metallization and also some other coatings on top of the surface, but still you need to start with a very good surface. And so really silicon carbide ticks all of these boxes, and that's why we're using it. It's very lightweight, it's very stiff, it's very strong, and it can be polished to very, very low surface roughness. Typically here you have a small part that we did when we did our first prints with silicon carbide. After printing, debinding, sintering, we did some polishing, and we went down to a surface roughness of 10 nanometers, which is really excellent and which is good enough to make afterward metallization and to make a mirror out of it. So that's the first application. Of course, we try to find other applications. Second one is in defense. Silicon carbide is used as an armor material. It's also used on ballistic, other ballistic applications because it's a very light material and it's very hard. And that's basically what you're looking for. You need a lightweight and hard material. It's already used with standard shaping process. And of course, we don't aim here to replace those standard shaping process, but you may need some complex shapes from time to time that does need to have these properties, that does need to be either ballistic protection or other ballistic applications. And in that case, 3D printing could really make sense in the way that it will allow you to make these complex shapes in the volumes you need, and really with the same mechanical properties as what you have with a normal silicon carbide, especially with the same hardness. We have a few applications in energy and especially in nuclear power. It could go in other directions, I'm sure, but nuclear power is a place where silicon carbide has really a sweet spot because it's very high temperature resistance, it's has a good thermal conduction, and it's corrosion resistant, and that's a set of properties you don't have with a lot of materials. So that makes a few obvious applications. One of them being heat exchangers. I didn't mention that it's also a material that withstands reasonably well radiation, and of course in nuclear that's important. And here we can understand the interest of using 3D printing. Typically, if you want to do efficient heat exchanger, 3D printing will really beat any other process. And here you have an example of the kind of structure you could use in a heat exchanger, this being printed in this case with our silicon carbide. Well, that's it. That's the few examples of application we had. The product is very new, so we're still looking for a new application, and that's also why we're doing this webinar. Maybe some of you have some ideas of application that could make sense, and really you're more than welcome to ask your questions, ideally in the Q&A section if possible. Ask your questions and I'll try to answer them to the best of my abilities. Thank you very much. We'll switch to the questions. I have one for the moment. So the question about surface roughness. How's the surface roughness in terms of optical mirrors? It should be less than microns. So that is correct. You need, I think I answered it later on, but you need to be to extremely low surface roughness. So the material itself needs to be in the range of 5 to 10 nanometer in surface roughness, which is really already quite amazing. And then the rest is usually done by applying what we call optical layers. So you actually apply a coating on top of the material. So material is here as a backbone, but you still have an optical layer on top of it to get really to the nanometer range or less than nanometer range in terms of surface finish. So quite a simple question about why are the green parts not destroyed during debinding? Well, that's quite a good question. Might seem obvious to those who have already some experience of ceramic manufacturing, but that's a good question. So I'm going to go back to some slides that were around here. here, which shows you the several steps of debinding and sintering. So as I told you, you start with a part that has a binder and powder. So clearly you could say, fine, at that stage I understand how that works. Then we'll do a first debinding that removes part of the binder. This is done with a solvent, and it will remove most of the soluble binder, maybe not all of it, but most of it. At this step, again, you still have what we call the backbone. There's a small misspelling here. The backbone binder, which will hold the particles together. So you may say, okay, we understand how that works. It's still a very important step, because by doing this debinding, we are already removing some significant part of the binder, and also we are already creating some porosity in the part that will help with the thermal debinding. And then the last stage is thermal debinding. So what happens is you're basically burning the binder away very slowly, because if you go too fast, you clearly are going to destroy your part. So you need to debind extremely slowly so that you don't damage your part. And once you have done that, once you have done the thermal debinding, at that stage, the part is extremely fragile. So the particles are just holding together by mere contact forces. So if you just manipulate the part, you will break it. At that stage, you can't manipulate the part, which means when we do thermal debinding in a furnace and sintering in another, we actually put the part on setters, and we will move the setters, but we won't touch the part, because at that stage it is extremely fragile. I hope that has answered your question. So do you also have mechanical properties and results with your samples? So this is still an ongoing process. We're still working on these mechanical tests. The first tests we've done are related to hardness and density, where we can say that we have really same properties as the bulk material. We will probably, out of experience with other materials, we will probably see a slight difference between printed silicon carbide and silicon carbide done by traditional means in terms of bending strength. We usually see a slight offset, typically a bit lower than the bulk material, something like 10-15% lower, especially in the Z axis. So is there a risk of collapsing during the binding and sintering steps? So that would really depend on the materials. When we talk about metal, yes, metals have really problems of collapsing and deformation because your sintering temperature is relatively close to your melting temperature, so the metal is soft when you sinter it. In the case of silicon carbide, not at all. The risk is more cracks, possibly deformation due to shrinkage, but I would say number one, cracks are the number one risk, but certainly not collapsing, because the silicon carbide is just a material you don't melt, silicon carbide, and so you don't have this risk of plastic deformation. So there's a question from Fernando. Hello, Fernando, by the way, about better performance of SiC compared to silicon infiltrated SiC. Is it generally always better, or for which properties? So that's really a good question. Because of course silicon carbide, silicon infiltrated silicon carbide, or reaction bonded silicon carbide is still a very good material. In some cases, it may be the right material for you. And for instance, I would say that both materials, the dense version and the silicon infiltrated version, both materials are quite good for thermal shock, because they have good thermal conductivity, they have relatively good strength and tenacity. So I would say both materials would behave well for thermal shock, but for instance, you will have a much lower temperature limit with a silicon infiltrated SiC because you have silicon in it. So you can't get too near the melting temperature of silicon. So that will limit the maximum usage temperature, probably around 1200, maybe 1300 degrees Celsius. But if you're lower than that in temperature, well, it certainly is an option. So a question from Mohammed about silicon carbide. So you're working on SLS of SiC. Well, that's another interesting way, difficult but clearly interesting. And you're asking if we have problem of SiC decomposition. Well, in our case, not so much. We don't have much problems of silicon carbide decomposition. I guess it is logical if you're doing SLS because you're actually giving a lot of power on a very small zone, and so you can decompose a bit silicon carbide. In our case, we haven't experienced too much problem with that. So did we measure the raw roughness of the filament without any polishing? So I would say the roughness of the filament itself wouldn't make really sense because it has to be printed, but we could measure the surface roughness of the parts just after printing, and I'm sure that's what you were suggesting. So we haven't measured it, but again, we've done that with other filaments, and the roughness just after printing clearly is not very good because you have layer lines, and these layers will increase the roughness. So we print with layers of 100 micron, but that still makes significant steps. So you can play a bit. Typically, if you want a flat surface, you can print that surface on the bed, and there you can have very good surface roughness. If you use a glass bed, for instance, you'll have a very nice shiny surface on your part, but that is limited to that printed surface. The good thing with ceramic is that the material is, let's say, reacts very well to polishing. So we usually don't focus too much on polishing before sintering. We sinter the part and then we will go to polishing because we know that it's going to work well here. And we typically use polishing methods like flat polishing if it's a flat surface, or tribo finishing for more complex geometries. So did you perform any mechanical performance evaluation? I think I already answered that one. Yes, for hardness and density, and not yet for the rest. So what is the density of the printed filament? So that's a good question. I must say I don't have the exact value on the top of my head, but I would say something like 2 point something, because the density of silicon carbide is 3, and you have a mixture of silicon carbide and the binder, so it's 2 point something, and it's certainly probably in the datasheet if you go on the website. I think so. So you mentioned only pure sintered SiC, if I'm right. How about liquid phase and nitride bonded or CSIC? So I did try to mention some of these, saying they exist, and they're clearly interesting options. In our case, we decided to focus on the dense and pure sintered silicon carbide. I think liquid phase is very interesting. Silicon infiltrated SiC is also a great material, but for instance, if you go for silicon infiltrated SiC, there are other options on the market. You can print it with binder jetting, and you'll have a porous silicon carbide, and then you infiltrate it. And so we felt that with our technology, we were bringing something more unique if we were doing the sintered SiC. So absorption of antibiotics on silicon carbide. I must say I don't know. I would say that I don't have a lot of experience of silicon carbide being used in medical. I would rather go for alumina or zirconia, which are materials that are extensively used in the medical industry, and they're used for implanted devices. So I would say alumina or zirconia would be safer choices. And we have not experimented at all with antibiotic absorption, but I know that there are a few implants on the market, and I'm thinking about an alumina implant, for instance, which is an alumina sternum implant, which is developed by a French company called iCeram, where I know that they have absorbed some antibiotic into an alumina implant. So I would say it's probably possible, but a bit far from our field here. Of course, one of the interests of additive is you could print porosity, and then you can use those porosities to have small reservoirs for antibiotics. Can it be printed with a 0.4 millimeter nozzle? Yes, it can. We usually use 0.6, but 0.4 is completely possible. We've even done a few 0.2 prints with zirconia. I don't think we've tested it yet with silicon carbide, but possible, yes. So question on price. So the price is anyway on the website, so there's no big secrets. Really, we're very open about our pricing strategies. If I'm correct, I would say a spool of 500 gram must cost something like 300 euro or 350. I can't remember. Of course, there are some possibilities to lower a bit that price if you hit volumes, but that's the price for one spool of filament. Will there be voids between deposited filament, and how can this impact on properties? Question from Hassan. Well, it really depends how you print. If you want a dense part, it is possible to avoid those voids. I think we did a webinar a few months ago, which was talking about this. Maybe if you scroll down on our YouTube channel, you'll find it. But basically, we've done some extensive testing on a few materials, and we saw that the printing parameters allow you to avoid these voids if you want to avoid them. Clearly, if you leave voids, you'll have an impact on mechanical properties. Properties will be less good, especially the bending strength. But then it might also depend on what you want to do. There's a very interesting publication on that by the Technical University of Liberec, which has been using our alumina filament to print test bars for bending strengths, and they played a lot with printing parameters, CT scan to see if there are some porosity remaining, and mechanical testing. What they have shown is that you can get to very dense and very strong material, typically with values that are as good as a standard bulk alumina. They have shown also a very interesting result was that they actually have almost the same mechanical strength with a fully dense bar, or with a bar where they actually print a bit of porosity in the middle of the bar, and they went down to infills of 80%. The outside of the bar was fully dense, but the inside was dense only at 80%, and they still had mechanical strength which was very similar to the 100% dense bar. So that's an interesting application of additive, of course. So what kind of maximum temperature can it sustain for gas turbine applications? I must say I'm not 100% sure here. I would need to dive a bit into it, but I can say that a silicon carbide that has been sintered in the best conditions If it is not in an oxidizing environment, and I would say gas turbine is probably not oxidant, you can go up to probably 1900 degrees Celsius, maybe a bit more than that even. A question about nozzles we are using for printing. So that's interesting because everybody keeps asking this question, wondering if we're using diamond nozzles or whatever. Actually, we're still using brass nozzles. So that's really the standard from the market. And you would have the impression that these materials being very hard, they're going to be they're going to wear down the nozzles very fast, but that's not the case, at least not so much, because the particles are very, very, very small. Typically, the particle size we're using for silicon carbide is much below 1 micron, and that reduces the wear we have on those nozzles. So we still use brass nozzles. Clearly, it's a consumable, so that means from time to time we have to replace them. But we still use brass nozzles. We have a few customers who are using hardened steel, which also gives great results, but it's not necessary to go absolutely for the most highest performance nozzle on the market. So how long does it take to do the full post-processing, such as debinding and sintering? So what actually takes time is debinding more than sintering, even though going to 2200 also takes a bit of time, but most of the time is in debinding. If you want to be on the safe side, you will calculate 3 to 4 days. It's actually a bit less than that, but you should calculate 3 to 4 days between debinding, which is going to take almost 3 days, and sintering, which is faster, but still you need to go to 2200 degrees Celsius. Well, of course, if there are any other questions, I'm always happy to answer them. I think that's all for the moment. So if you don't have any more questions, I think this will close our session for today. Again, very happy to have had this session today. We're extremely excited about this material. We feel there's a very, very strong potential in the industry, and we're welcoming any idea of application you may have, besides those I have already cited, of course. So feel free to reach out to us if you want to know more, or if you want to discuss your applications. Thank you very much.